So this is the third lecture of week number 10, and in the previous lecture we had gone through two problems related to the air conditioning part of this course, and we will go through another problem in which I will go through the solution procedure, and then you can apply that procedure to the problem and obtain the desired results. So I will put up the question on the screen and then go through the solution procedure. The problem relates to a terminal reheat system for two zones in which information pertaining to the outside design conditions, the respective zone design conditions, and some other information is provided, and based on that information we are asked to find out the supply air mass flow rate for the two zones and the reheat capacity for each of the zones and the cooling coil capacity. So remember, in a terminal reheat system you have a reheat boxes or reheat terminals before each of the zones, and according to the requirements of the zone you will provide the reheat for each of the zones that you are conditioning. We have discussed this type of a system earlier, and I had also given you the cyclometric diagram of this cycle, and that is what we will start with. We will go back to that cyclometric diagram in which the terminal reheat cycle is sketched, and then try to see how we will proceed with the solution. You can see the schematic the cyclic representation on the cyclometric diagram. We have the two zones, zone A and B, for which if you look at this point 6 or 7 or 1, they are all the same states, and when you refer to the schematic diagram of this arrangement, which you can refer to from the earlier lectures, you will see that this is the state at which the conditioned air leaves the cooling coil, and then that air will be reheated as per requirement of each of the zones. So for zone A you will reheat it from state 6 to state 1A, and similarly for zone B you will reheat it from state 6 to state 1B. Then that air will be supplied to the zone where it will balance the heat gain, both sensible and latent. You can see the load ratio line for zone B, and there is a load ratio line for zone A. The same two lines are shown on the protector over here, so these lines would be parallel, and we can try to see that these are actually the lines that we are looking at. For example, if I look at this line, that has the same slope as the slope for zone A, and the other line then should be the line which shows the slope or the direction of the process for zone B. And when the air exits the two zones, that air is combined into a single stream, which is shown by the state 2 or 3. Then that stream is mixed with the outside air after part of it is exhausted, and the rest is recirculated and mixed with the outside air, which is at state 4. Then the mixed air conditioned is at state 5, and then that air goes to the cooling coil, so there is the cooling and dehumidification process shown over here. And as I said earlier, when we solve problems of this sort, what we should try to do is to first obtain all the state points, and then we can complete the cycle on the psychrometric chart. And while we do that, we might obtain some intermediate results, and when we have completed the cycle, any other remaining results can be obtained from there. So let's start with the problem that we have been given and see which states can we locate and then how to proceed onwards. So we are told that the air, when it leaves the cooling coil, is saturated and it is at a dry bulb temperature of 15 degrees C. So because it is saturated, only the dry bulb temperature is sufficient. That is, you will mark state 6 on the saturation line corresponding to a dry bulb temperature of 15 degrees C. In this schematic diagram of in this sketch, it is not shown on the saturation line, but when you actually solve this problem, it will lie on the saturation line. So we might have state 6 somewhere over here. Let's say it is over here, and this is on the saturation line. I'll just try to extend it slightly. So this is, and this will be at 15 degrees C. So we've got state 6, 7 or 1, they are all the same. Then we can locate state 2A, because the design conditions for zone A are given as 15 degrees C dry bulb temperature and 40% relative humidity, and we can locate state 2A. The sensible and latent loads for zone A are also given, so we can easily find out the sensible heat factor for zone A, which is the sensible load divided by the total load, and that comes out to be 0.80. So we know that state 1A will lie on a straight line drawn from state 6, because from 6 to 1A and from 6 to 1B we have the reheating, and that is just a sensible heating process. So what you will do is that from state 6 you will draw a line of constant humidity ratio, and both states 1A and 1B, they must lie on this line. We have now located state 2A, and I'll just mark it off that we have got state 2A. Let's give it a different color. And also we have located state 6 or 7 or 1. So I will also identify that 6, 7 or 1, it's on the saturation line, so we will assume this is on the saturation line. So we've got these two states. Then, because we know the sensible heat factor for zone A, we can use the protector, and on the protector you will draw the line corresponding to a sensible heat factor of 0.8. I will just show it arbitrarily over here because this is not according to the data, this is just a general representation. So let's say this is 0.8, and what we have to do is we will have to draw a line parallel to this line from state 2A, and when you do that, it will intersect this line that we have drawn from state 6 at 1A, and that will establish state 1A on the psychrometric chart. So we can say that we have also located state 1A Then we can also find out the dry bulb temperature at this state. All you have to do is to just draw a line from over here, a vertical line, and that will give you the dry bulb temperature at state 1A, and I leave it to you to find out that value. We can now repeat the same procedure to locate state 2B and then find out the dry bulb temperature at state 1A. So we'll locate state 2B because the design conditions are given. Then we will find out the sensible heat factor, and again we will locate state 1B on the constant humidity ratio line, and that is the next step. You can see that on the psychrometric sketch I have shown these points that we have located. We started with state 6, located state 2A, used the sensible heat factor, located state 1A, found out the dry bulb temperature at state 1A. Then similarly you can see that we can locate state 2B because we are given the dry bulb temperature and the relative humidity. Then the sensible heat factor is also worked out from the sensible and latent loads. Once we have got those, we will use the protector and then locate state 1B, and at that state we can then find out the dry bulb temperature. So that is the way we can locate states 1A and 1B. We can also find out the mass flow rates for the two zones. Remember, the mass flow rate that is supplied to zone A will be the mass flow rate at state 1A, and similarly the mass flow rate that is supplied to zone B will be the mass flow rate at state 1B. And that is quite straightforward because we are given the sensible load for that zone. We can then easily find out the mass flow rate because we know that the rate of energy transfer is equal to the mass flow rate into the specific heat into the temperature difference for sensible heating or sensible cooling, and we can use that basic relationship to find out the desired mass flow rates to the two zones. Let's proceed further with that. Okay. So the sensible load for zone A is given to us. Mass flow rate for zone A is to be worked out. Specific heat for air will take the standard value of 1 kilojoule per kilogram Kelvin. The temperature T2A we were given, T1A we have found out, so you will find out the mass flow rate for zone A. And along the same lines you will find out the mass flow rate for zone B, and that is in kilogram dry air per second. And once we know what is the rate of mass flow rate to each of the zones, then we can find out the energy supplied at the reheat terminals. And the equation, because it's sensible heating, equation is the same, that the energy transfer rate is equal to the mass flow rate into the specific heat into the temperature difference. And remember, the air after the cooling coil is at a temperature T1, or you can say T6 or T7, they are all the same, and that air is heated by the individual reheat terminals. So it will be heated to a temperature T1A for zone A, and it will be heated to temperature T1B for zone B accordingly. So the reheat energy requirement for zone A is equal to the mass flow rate for zone A into the specific heat into T1A minus T1, and once you put in the numerical values you will get the desired energy transfer rate in kilowatts. And similarly the reheat for zone B can be found out because we know the mass flow rates and the temperatures are also known to us now. If you refer to the psychrometric diagram, you can see that we now have three states which are yet to be located, that is state 2, state 4 and state 5, and they can also be found out by applying energy and mass balances. So because state 2 or state 3 is obtained by the mixing of the two states, that is state 2a and 2b, we can perform an energy balance and that will give us state 2. State 4 is the condition of the outside air and that is given to us, so we can easily locate state 4. That leaves us with state 5, and remember state 5 is again a diabatic mixing of two states, that is state 2 and state 4, and again we can apply the energy and mass balances to locate state 5. You are given in the, if you read the problem, the amount of the recirculated air and the proportion of the outside air, so that information will be utilized, and of course we will need the enthalpies when we perform energy balance, and that will help us locate state 5, and that sort of an exercise we have done earlier as well in other problems. So you should be familiar with the use of that process in locating states 2 and state 5. And once we have got all these states, the only thing that remains to be found out is the cooling coil load, and for the cooling coil load we have the equation that we had used earlier as well. Of course the symbols are different this time, but the basic equations remains the same. That is, across the cooling coil the enthalpy difference is from state 5 to state 6, and the mass flow rate is the total mass flow rate that we have at state 5, which is the sum of the mass flow rate at state 4 and state 2. So, or we can say it is the sum of the mass flow rates of the two zones, m dot 1a plus m dot 1b. And then of course in this equation we have an additional term. Remember, this represents the energy that is carried away by the condensed fluid, and for that we need the humidity ratios at states 5 and 6, and we are assuming that the condensate leaves the cooling coil at the saturation condition of state 6. So you can find out the value of HF at 15 degrees C from the table, and then you will get the capacity of the cooling coil. So that is the procedure, and you can follow this procedure and obtain the values that are required in the problem. So that concludes the numericals that we were going through at the end of the course, and I will now go through a few videos to further show you some of the components that we have talked about. If you recall, in a central air conditioning system we have the plant room, in which you have the refrigeration system, you have the pumps, you have the hot water boiler, etc. And you frequently come across a term called the chiller. What a chiller is and how does it look like? Okay. Now that is something that I will show you by using a video. And actually a chiller is the entire refrigeration unit. That means it contains the condenser, the expansion device, the evaporator, and the compressor. And we will look at a video in which you will see the view of a typical chiller unit. Okay. So let's go through that video, and then we will move on to